In this video, we'll take a look at some of the introductory ideas of linear algebra, maybe give you a sense of what a big aspect of this course is all about, and introduce some terminology. Now, when you think of the word linear, what comes to mind? Well, if you think back to, your previous math classes, you might think of, lines, right? So straight lines, and you've done a lot with lines. You've worked in calculus, you worked with tangent lines, and you know a lot of properties about them. So you would tend to think that this course might have to do something with lines, and in some sense it does. What about the word algebra? Right. Well, if you go back, I mean, the word itself has a pretty rich history, and it basically, when you think about algebra, when you ask most people, what is algebra all about? They might tell you it has to do with, solving equations. Right? You learn all these rules and properties, but you're always solving for x. You're always finding x. Why is x always lost? Anyway, so it seems like if you try to put these two together, you might say, well, linear algebra is a course that involves solving equations with respect to lines or something like that, right? And in some sense that's true, but over the course of your study, that idea of linear algebra will be expanded. And what's not really here, you don't really get it in these kind of descriptions, is the concept of a vector. And vectors are going to play a huge role in this course, right? And not only that, but your idea of a vector will be, flipped on its head, maybe, right? Okay, so it's good to have some idea of what this course might entail, but I will encourage you from day one is to approach it with an open mind, right? But we are going to talk about equations, and we are going to talk about linear equations a lot, especially the first few weeks in the course. So let's define like what a linear equation really is in its most general terms, and then talk about what it means to solve a single linear equation, and then just kind of add to it, right? So a linear equation, right, in n variables, and that phrase might sound a little strange, but that's how it's stated. So a linear equation in n variable is of the form, right? And let me write something down. And again, this is a very general definition, just like how there's a general definition for like a polynomial. There's a general definition for a linear equation, and this is what it looks like. So I'll write it down, and then I will talk, about these symbols and so forth. Actually, let me do this. So a1, x1, a2, x2, plus a3, x3, and then dot, 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 plus a n, xn is equal to b, right? Yep, so this is what we're going to call a linear equation. The xi's are our variables. So in this general definition, what I've written down is a linear equation that has, if you count them, it will be n variables, and that's what we're describing with this phrase right here, right? So x1, x2, x3, dot, 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 xn are all variables, right? Or you can think of those as our unknowns. The x, right, so the xi's are our variables, and then the a's, what are these a's? Again, with subscripts. So the ai's, these can be any real number, right? And we call those the coefficients, right? So these are our coefficients because they're multiplying our variables, right? And then b on this side of the equation, all by itself, is also can be any real number, and we sometimes refer to it just as the constant term, right? Because it doesn't have a variable. Again, like I said, it's all by itself. So this is the constant term, right? Let's see. The a1 x1 is referred to as the leading term, right? Why? Because it's the first one in the equation. So this is our leading term. The a1 by itself, so this, not surprisingly, is called the leading coefficient. All right, and then you have the other ones that are not leading, right? So that is a the general definition of a linear equation. So let me just take a few minutes and do some examples and say, okay, this one's linear because it fits our definition, and then this one isn't because of this particular reason. And then you'll get a good idea of what's linear, what's not, right? Okay, so well, I guess, yeah, these are just some examples. And let's start with this one. So, if you have something like 2x1 minus 3x2 minus x3 equals 0, this one is linear, right? So this single equation has 3 variables, right? x1, x2, x3. We can see nice integer coefficients, 2, -3, -1, and then the constant on this side is 0, right? If I think what I should do is maybe change just maybe 1 or 2 things in each example, just to show how this definition is very specific. So for instance, in my second example, if I take x2 and instead of multiplying it by 3, if I raise it to the 3rd power and then keep everything else the same, this one is non-linear because if you look at in our definition, every variable, the only exponent that it has is an exponent of 1. None of the exponents are written, but it's understood that there's a 1 as an exponent of every variable. So in this equation, x2 is being raised to the 3rd power, so that makes it nonlinear. It doesn't fit this definition, right? So because x2 is being cubed, right? And that makes it non-linear. What are some other things that could make it or make an equation non-linear, right? Well, in this case, if I have the term 2x1. What if, and just to show you that I don't necessarily have to always have my variables as subscripts. So let me kind of change the way I'm writing my variables, and let's say I have something like e to the x minus y plus z is equal to 10. All right. Well, in this case, the e here is our exponential or logarithmic base, base e, that very important number. So that's a constant, that's a real number. But the problem is I have a variable as an exponent, and I'm not allowed to do that. So this one is non-linear. Right? Why is it non-linear? Because of the e to the x term. Because of e to the x. We can't have a variable as an exponent, right? So we have a variable exponent. Not allowed, right? Like I said, the only exponent that you can have in a linear equation like this is an exponent of 1, right? And let's just do a fourth example. So something like, I notice here, by the way, in my third example, that since I only have 3 variables, x, y, z, again, you can use x, y, z. You can use x, y, z, w when you have a smaller number, quote unquote, smaller number of variables. You don't necessarily have to use the x followed by or in conjunction with subscripts, right? So get used to seeing sets of variables where you have a single letter and then you indicate different variables using subscripts, or if you don't have that many variables, you can use x and y, you can use x, y, z, you can use x, y, z, w, right? One more example just to show you a couple things. So let's say I have pi, well actually I'll do 2 more examples. Pi times let's say x, and then plus the cosine of 2 times y, and then minus e to the 10th power times z is equal to the square root of 79. All right, so I'm picking some not so commonly used numbers, but let's see if this actually fits the definition, right? In fact, what I'll do, I'll write out, the coefficients using the AI notation. So a sub 1 is equal to pi. A sub 2 is equal to the cosine of 2. A sub 3 is negative e to the 10th. And then my b, right, that constant, that lonely constant on the other side of the equation is the square root of 79. Well, are these real numbers? Yeah, these are real numbers. They're all irrational numbers. Some of them are not just irrational, but they're transcendental numbers. Yeah, but these are all real. And that's fine. That we are allowed to use any real number as coefficients of our variables, and then constant terms, usually in the organized on the opposite side of the equation. So that's fine. And then our variables, right? So our variables are x, y, z. And again, none of them are exponents, right? None of them are raised to any power other than 1. And these are good. Yeah. So this equation, even though when you look at it, you see a cosine function, or, you see a cosine function, but you're taking the cosine of a number, right? So that makes it a constant. Same thing, you see the e, but it's not e to a variable, right? It is just e to the 10th power. It's a big number, but it's just a constant. The square root of 79. Yeah, the square root itself, if you think of the square root as a function, it's non-linear, but you're not taking the square root of x or y or z, you're just taking the square root of 79. So yeah, this equation here is linear. right? We might not work with, pi and cosine and sine and e and ln a lot in terms of, like irrational numbers. We might do a lot of work with just integers, but there's nothing that precludes us from having irrational coefficients. So this one is linear. For my fifth example, let me change one thing here, and so I'll keep the pi x, that's fine. If I were to switch the 2 and the y, so if I have it like this, plus 2 cosine of y, and then let's say we did this. Let's say I switched the 10 and the z, and then I'll just put the 10 in front like this, 10e to the z, and then let's say I kept the square root of 69. Now this is non-linear. And it's non-linear for two reasons. One, we are not allowed to take not just cosine, but any trig function and apply it to a variable. The only thing we're allowed to do to a variable is to multiply it by a constant. So we can't have, right? In fact, let me put a big red X through this. We can't have the cosine of a variable. We can't have, as we said it earlier, e raised to a variable. So because of these two terms, the equation is non-linear, right? And this course is a course that will involve only work with linear equations, right? So there really isn't a course like that's called non-linear algebra. I mean, the stuff that you did in college algebra and trig, you worked with non-linear functions, right? So you were doing a lot of that work. Now what we're going to do is we're going to do a lot of work with linear equations and kind of expand what you think of linear equations. So that's good. So it's very important to be able to identify linear versus non-linear and make those distinctions very clear. Now, as we said, algebra tends to be the study. A big part of algebra involves solving equations. So let's write down what it means to have a solution, right? So a solution to a linear equation. So a solution to a linear equation, right, is a set of values. So is a set of values where, like, your x1 is, let's say, c1, x2 is c2, ... your xn is equal to cn, right? So it's now when you talk about solving a linear equation, what you've found are values, or at least, let's say values for each of your variables such that this is true. If I take the first constant and then multiply it by c1 and then add to that the second constant times c2 and then add to that, so basically plugging in these numbers, these c's, c1, c2, cn, for the x's, plug those into the left hand side of our standard equation. When you do this arithmetic operation, you have to end up with your b, right? So in other words, a solution is a set of values for your variables that make the equation true, right? And that's what you do. It starts out where you learn how to solve linear equations where there's just one variable, right? This course will give you tools to where you can solve linear equations of 1,000 variables, right? In theory. Now let's just do a couple examples here, and I'm going to use this example to introduce. I think from the very start, there's a very key concept that we will utilize throughout this course many times, and it's good to see it right away and then start getting used to it. So let's take a look, and I'll use a simple example here to illustrate this concept. Let's just use a linear equation that has two unknowns. So let's consider 2x plus y is equal to 6. Right, so let's look at something like this. This is definitely linear, right? It's one equation. It has two unknowns. We can see the coefficients on the left-hand side, and we can see our constant right here. So let me ask you, so think about it for a second, and maybe you might even pause the video, think about it, and maybe start scribbling some stuff down on your own. But what are some solutions, right, if any, right, to this equation? Right? So what are some of the solutions, right? And remember what the solution is. It's a set of values that we can assign to our variables that will make this equation true. So if I, for instance, said, if I look at it closely and say, well, if I let x equal 0 and then let y equal 6, will it work? Because I would have 2 times 0 plus 6. That's 0 plus 6. That's 6. And that works, right? So again, if I were to let x equal 0, then y would have to be 6. If I were to assign any other value to y, I wouldn't have a true statement and therefore wouldn't have a solution. But then maybe someone else, maybe even another person watching this video at this very moment would say, well, if I were to let x equals 3 and y equals 0, that should also work, because I would have 2 times 3 plus 0, right? So that would be 0, and then that would give me 6 plus 0, and that's 6. So that also works. And then you start thinking, well, I could go on forever, because it's like I have one equation, but there are two variables here. So as long as I choose my x and y carefully, I can't just pick I can't assign any old value for x and then any old value for y. If I'm a little bit strategic in how I assign my variables, it looks like I can keep coming up with solutions. So for instance, here's another one that you might not think of right away, but it's any set of values you can find. So like if I let x equals 1/2, and if I let y equals 5, then what I will have is 2 times 1/2 plus 5. That will be equal to 1 plus 5. That's equal to 6. And then this is like, okay, now this is getting interesting. So let me just show you how interesting this can get. If I let x equals pi, right? So if I did that, and if I let y equals 6 minus 2 pi, would that work? Right? These are numbers. I'm just, notice what I've done. At first, I looked at some integer values. They're really obvious ones. And then I said, well, let's look at a rational value for x. And we got a nice integer for y. But let's see what would happen if I assigned x a value of pi and y a value of 6 minus 2 pi, right? So let's check to see if this works. So if I take 2 times my x value plus my y value, 6 minus 2 pi, well, what do I have? I have 2 pi plus 6 minus 2 pi, so the 2 pi cancels out, and I'm left with 6. So yeah, I forgot my check mark there. But we have another solution, and I feel like I could just keep going on and on and on and on. In fact, this one should really give you a clue as to the process that we could probably use to describe all the possible solutions to this one equation. In other words, instead of saying pi or a half or 3 or 0, what if I said, so let's say this: if x is equal to t, any real number, right, then I could figure out what the y variable would have to be in order to make the left hand side balance out and give me 6. But I could do it in a symbolic way. I don't have to do it with specific numbers. In fact, I can't continue this process forever, right? Because there are infinitely many values I could pick for x, and then I could find the corresponding values for y. In fact, later on, very soon, we're going to look at a geometric way to interpret this and other things, right? But let's go back to this and finish this idea. So if I let x be any real number, right? Then what that means is then y would have to satisfy this, right? So then y must satisfy this equation. It would have to satisfy the equation 2t plus y is equal to 6. And if I solve this for y, it tells me that the y that would correspond to this x would be 6 minus 2t, right? So now what I could say is, just like how I was kind of writing these as, I didn't write them as ordered pairs, but I paired them up. Like the x equals 0 would be paired up with y equals 6. The x equals 3 would be paired up with y equals 0, and so on. I could say whatever x I choose, let's say I choose a value of t, that would have to be paired up with a y value of 6 minus 2t, with the understanding that t can be any real number. And this is how we can, in a very nice way, describe the solution, all the solutions to this simple linear equation. And this, so let me show you. So you can certainly write something like this. This is fine. Let me give you an alternative way in terms of, if you think back to algebra when you were writing down solution sets, there was that set builder notation. So here's an alternative way. You could say that it's any ordered pair where your x value could be anything, right? Anything real. And then the y value would have to be 6 minus 2 times whatever you chose for x. So it's like you have the freedom to choose anything for x, but once you make that choice, you then have to balance it out with the correct choice for y. And then we again specify that t can be any real number, right? Both of these are referred to, there's a special name, so this is called the parametric, nice fancy word, the parametric solution set of our original equation, which was the 2x plus y equals 6. Parametric solution set is something that is used to describe equations that have infinitely many solutions. And we refer to t, right? So this t that I'm saying could be anything real, that is called a parameter, or it's called a free variable, right? So we refer, I'll do it on this side. So we refer to t as a parameter or a free variable, right? And you're gonna deal with this idea, I mean, constantly throughout the course, in the sense that you'll be working with sets that consist of infinitely many values, and you want to find a nice, an efficient way of describing them, and this parametric way is very, very useful, right? So I think that is a good place to stop in, in this particular video, and we're certainly going to build on it in the future. But hopefully now you kind of you get a sense of some of the things you'll be doing, and as I've said, this idea of a parametric solution set, it's going to be a consistent theme throughout this course, and it will enable us to solve so many problems. It's amazing, right? So hopefully this kind of whets your appetite, and I hope to see you in another video.